Well, hello, folks. I think we'll go ahead and get started. Let me go ahead and open up in prayer, and I'll give you a sense of the things that we're going to be covering today. So, dear Heavenly Father, Lord, thank you for the chance to be working with each of the students in this course. Lord, I pray the material will be clear. I pray it can be an enjoyable process of getting familiar with computer architectures. And this is going to help each student to get the career of their choice or opening the business of their choice. I also pray that you would help them in their spiritual formation, Lord, that all the time that they've been able to dedicate to studying scripture will be things that they're going to be able to cherish in their heart and utilize in their day-to-day situations that come up, and understand the theological concepts we derive from that to guide ourselves. And finally, Lord, give them interesting and creative ways for faith integration. In Jesus' precious name we pray. Amen. Okay, well, today we're going to continue on with some of the discussions we were talking about Tuesday as well as last Thursday. And so we're trying to get a better sense of like, well, how would we build a computer system? And we got a chance to be thinking about this from the arithmetic and logic perspective. We talked about numbers, we talked about how we do computations, how we have like floating point numbers. You can think of like scientific notation. And so we have things like that. Then we have this chapter on digital logic. And before we get into that, and I'll probably defer this until next Tuesday, I wanted to get a chance to be thinking a little bit more deeply about some of the things that we're trying to accomplish. And so I wanted to be thinking about that from a processor perspective. And so there's a couple other charts, a couple other presentations that I'm going to spend a little time to go over. And so the first one I wanted to talk about is to talk about the arithmetic logic unit. And the way that I'm going to introduce this is through a chip. It's been around for a while, a 74181, and it gives you an idea of how you can do this computation. So an arithmetic logic unit is the core feature that we're doing that we need to do when we think of a programmable device that can do all kinds of operations. And so you can think of it like the Swiss Army knife of a computer. And so what we have is we have two operands that we do something on based on a certain type of a code, and then we get the results, and if there's any status that comes out of that. So let's think about this 74181, and I have a couple of charts that give you some ideas of what it looks like. And so this is what an IC looks like for this. And so it actually has 24 the wires that go into a socket, and then you could be having that connected to other devices. And so there's inputs, there's outputs, you have you call this A and call this B. That's the way that they have this. And so A, and then they have B. They also have some control information that's helping us to figure out, well, what is it that we're asking this to do? All of that is included here. And so this just gives you an idea of how it would look like from a chip perspective. And now will be a little bit complicated, but I'm going to try and unpack this so you can get a chance to be seeing this. And so we have 4 bits to determine what we're going to ask this programmable device to do. So this P code, this would be an example we're going to be getting into in the next couple chapters. We're starting to look at things in assembly language, but we wanted to start to figure out, well, each one of these things mean something, add, load, store, things like that. So if we have 4 bits, how many different types of commands do you think we can have? Anybody want to venture a guess on that? 2 to the 4.
Like 16?
Yeah, correct. And so if you count this up, there's 16. And so they're using this low and high nomenclature. We could have had this 0 was a low and a 1 was a high. And so basically it goes from 0, 0, 0 all the way to 1, 1, 1, 1. And so we can either do logic functions or we can do arithmetic operations. And so the first type of control for extending this past these 4 bits is you have this one, so you have another bit that's either 1 or 0. So here if it's a 1, it does logical functions, and if it is a 0 or a low, it does arithmetic operations. Then we also have one other thing here, C, and so when it's high, this means that there's no carry, and when it's low, it means there is a carry. Now, I'm not going to go through all of these in detail because that's not what I'm trying to convey with this quick introduction to an arithmetic logic unit chip, something that's in a modern day CPU, but maybe you're not aware of that. So let's just take a few of these things. So we can do addition. That would be one thing. We can do logical operations, and this is where it gets a little bit confusing if you're not familiar with it, that there's these expressions that look like addition. And so you just have to remember what these are. And so A, B is and logical, like an AND gate. And then a plus is a logical OR. So those are some things over here. Here we can do addition A plus B. We also can be doing multiplication, and there's a couple more complications here. I'm not going to get into why they have this -1 and what have you. So let's just genericize this to be thinking what we can do. So we can do logical operations, we can do arithmetic operations, and so there's actually 4, 5, 6 bits that determine the characteristic of what this is commanded to do. And just to give you an idea, this is what the guts, if we express that in terms of digital logic, all of those functions that I just mentioned. So we have the inputs, you have input A, input B, those 4 bits. We have these control lines. So we saw that over here as 0, 1, 2, and 3. And then there's some other information like this M. This was another bit that goes in. And and then they have this carryover device here, which was another thing that we have here. So they're roughly equivalent. I got these from different sources, and so there is maybe not completely a one for one this, but here, okay, we do have that the CN here, but then we have this other one here, which is the carry out. So that's the first level of giving us a perspective of what we're trying to do with our computing environment. A core feature of the processor is the ALU. And any questions on that? You guys tracking with what I'm trying to accomplish? Let you see in a little bit more detail what's going on in the arithmetic logic unit.
Professor, what did the M mean?
This N,
No, sorry, M.
that's just another control line that exists for this. That's how you signal either going to arithmetic or logic. That's what that is trying to indicate here. So either you're doing logical functions or you're doing arithmetic functions. Does that make sense? See that?
Yeah, so, okay.
Any other comments or questions? You can give me a thumbs up if you're tracking what we've got here. Okay, so I'm trying to give you a survey, but a detailed survey of these different things that exist. And there have been a few questions about why are we using the MIPS for our assembly language programming, and we're going to have plenty of lectures coming up on this, but I'm just going to be showing you a few slides from a larger slide deck here, just to make a few points to help you see that. And so the MIPS and instruction set, it's a fixed length. And so here, 32 bits, and eventually they upped it to 64 bits. And so every command, every assembly language instruction is either 32 bits for a legacy mode or 64 bits for a more current. And so these are the kind of things that we can be doing. We can do arithmetic and logical instructions. Remember, that's what we're thinking about in terms of the arithmetic logic unit. We can do branch. And so this was a question that came up. How do we do like an if or a while? We don't have those things. If there's something at a more basic level, you do a comparison of two registers. And if it's less, or equals, then you go to one location, otherwise you don't. And so you do have these basic type of decision-making things that you can do. You can load an instruction, so you can go from memory, put it into a register. You can jump from one point in your program to another. You can store, you can take something from a register and put it into memory. You can do data movement, moving things from one point in memory to another. And there are some interruption type of operations that exist. You can do comparison. You can do constant manipulating instructions. And so those are some of the things that are available. And you can see how MIPS over time has evolved: MIPS 1, MIPS 2, MIPS 3, MIPS 4. And as with everything else, 32 bits was no longer adequate, and so they jumped it to 64 bits. Intel had a 32-bit architecture, now has a 64-bit architecture, and one of these days, I'm sure it'll be moving to 128. So I'm not going to go through this, but this is just a blow up of showing the arithmetic and logic instructions. So you can see that there's various types of add. I'm not going to get into that at the moment, but we're getting a chance to see a little bit of this as we get into our Mars emulator. You can do division, you can do multiplication, you can do subtraction, you can do logical operations or and. Those are all possible, and this just is give you an idea of that. So this is once again a blow up of these other type of instructions. I showed you them on the previous slide, so I won't focus on this at the moment. And then the branch, jump, load, and store instructions, just it's a little bit more readable on this slide compared to the others. So I'm just going to end with this and then one more slide. Remember, we talked about that for the ALU, that chip that I showed you, there was actually 6 bits. There were 4, but then there was some other control things that were also utilized. And so now, for a part of this 32 or 64 bits, you have to have these certain types of codes to be specifying what's called the opcode. And so thus you can program your arithmetic logic unit to do an add or to do a subtract, to do a logical or. These are all things that you can see just literally by changing one bit. You can change the characteristics of what you're doing in your ALU. This is just an alphabetical summary of the MIPS commands. And so I'll just leave it at that to let you see what we have there. So basically, what I've done is I've tried to give a little bit of a context for first of all, thinking about an arithmetic logic unit. This is a key element what we have in our computing system. And I was referring to a chip, a 74181. And I, in the past, have offered credit that if somebody wanted to do a digital logic design of this, I would be very happy to give you extra credit so I could fully have that implemented. I think I have found something like this, but I haven't shown it to you. Some of these more complicated circuits in the digital logic designing that we're doing goes beyond what I'm trying to have us all get familiar with. And then that's one level. And now, not only do we have to be thinking about the arithmetic logic unit, we have to be thinking about a larger context of types of commands. And this is what we're going to be getting into when we start talking about instruction sets. And so you can keep that in mind. So here, when we're dealing with the Mars MIP emulator, we're focusing on this. The arithmetic logic unit is the key thing. We have the registers, and then we have the ability to get in and out of main memory. And so that's the focus that we have there. Any comments on that?
I was wondering if like later on and during the like in the weeks of working on the second project, will you like kind of present us like ideas that we could try to go like try to that would like help us like start on the on our programs for Mars like based on our themes? Like just kind of like what you did for the first project.
Yeah, and I'm pulling up this program here that we went over last Thursday. I'm going to spend some more time talking about here and try and reiterate how something basic, well, this is maybe not basic, but maybe intermediate. A basic one would be like hello world, what you're trying to just print out hello world to the console. That would be something that you could do. So let's go back to this and think in the context. Okay, so now we were talking about an arithmetic logic unit that you can be programming that. A higher level here is these MIPS instruction sets. And so there can be a little bit of variation from one vendor to another. Say, for example, you have an ARM type of processor. Well, what we're using for this is this instruction set. So it's for the most part, it's going to be close to just about any of what we could find on the internet. So, but this is I think it's in alphabetical order. And so this shows pretty much the lion's share of what you would be doing. And let's begin to think about how we could be generate a program that's related to your project. Okay, so this example, what it does, it takes two numbers and it adds them, and it also does the subtraction. So let's take this at one step at a time here and think about this. And so how would this relate to a project? And so we have we're doing something here where we're interacting with the console. That could be a way of mimicking you having an input. And so a sensor provides a result or something like that. And then it needs to get into the CPU for it to be doing that processing. Well, I'll just run this regular speed just to give you an example. So let's look at adding a couple numbers. Somebody want to give me a number? Okay, 24. So that would be our A. And how about for a B? Someone else want to give a number that they'd like to try? 25, okay. Okay, so A plus B is 49. Let's go ahead and do this in single step mode now. Let's go, I'll go over to the okay, that's going back. Go all the way back. So the first thing we want to be doing is we have to be doing a syscall for each of these things. So we load the registers with what we want, having these inputs, having the command that goes in, and that is going to do the results. And so it just gives you an idea that we're seeing here in this way of having this this emulation. Last time we talked about the main headers, the dot text. So if I just go back to this, to the directives, subsequent items, instructions stored in text segment at the next available address. So this gives an idea where to be putting it within the memory that's available to the CPU. We have the dot global. So the dot global declares the listed labels as global to enable reference from other lot files. So here we have main. So we have like our main part of our program, which should be familiar with you all doing Java programming and other languages. We have the dot data. It's a subsequent item stored in data segment at the next available address. So we can see that we have text, we have data. And so here we're going to be storing 4 different types of ASCII related information. ASCII Z stores a string in the data segment with as a null terminator. Okay, so those are all the things that we have laid out here for us. So if we start to execute this one step at a time, so we want to printing a line to the string to enter a number. So here we're loading message 1. So here we have this information stored at a specific memory location. So going back here for a minute, this is like these things down here. So there needs to be a specific memory location, and I'm looking at the contents of those memory. So let me see if I. Yeah, so this is the location where the program is. This is the location where the data is. So they're in different locations. And so you can see the way that these things are listed here. You can see enter ENTER space a colon. And so these are not in the order that's the easiest for us to be reading English. But this is the way that this processor is set up. And so that's the order that we have to be using. You can see ENTR B colon. And so those are the 2 values here. So the first one is going to be pointing to this. And so we're going to see that it's going to show up on the screen. do the syscall, and this is where, okay, so enter A. You had 24 and 25. Okay, so it's printed to the screen, but it's not still ready for it to be reading from the console. So I have to enter a few more commands here. Okay, so I entered that. And it's going to read it. Now it's asking for the second one, 25. So we have those values. And then it's going to print out the message A plus B. Once we get to the syscall. And then it's going to, from the other register, get that total. Print that out. Okay, I think single stepping, it it got the 4, but it didn't get the 20, the 24. So that's why it's doing it's giving that value. So apparently I typed too soon and I was out of sync with it going single step. So sorry about that, but we did see that the first time when we ran it regular speed, it worked. Okay, let's try and have a little bit more focus on how this relates to your project. And who would like to share a little bit about the details of your project, and let's see if we can tie something like this in a way that would be helpful for that. And then there's another assembly language program I can show in just a few minutes, but let me just follow along with here. Let's see, maybe I'll just at random pick one or more people. So Connor, you want to give us some insight into what you're doing with your overall project, and let's see how we could start to align this with what we've got going on here. Let me pull up our overall project list. So this is a list that we're working on. I think Isaiah said he was going to revise this, and so I haven't updated this chart yet, but Connor, just doing a com check. Do you want to share a little bit about your project and we can see how this might work? Okay, Barak, you want to give us a chance? Oh, you want to give us some feedback and let's see if we can start to finesse this a little bit with your project? Okay. So thanks that you can use the chat, but if you want to just put in a few words about your project and let's think about how what we're doing here might relate to what you're coming up with, and we can see start to explore what kind of modifications might be necessary. I can read it for you once you put it in the chat. Okay, well, I'll come back to Brock because he can type that out when he's ready. Um,
Professor,
great. Yeah, yeah, Nathan,
could I share my project idea?
if you'd like.
Okay. So what I was gonna do is, I think it was number 13, which is the Sensormatic system. Basically, I just wanted to create a system of like inputs where if someone were to like, or it's based on motion detections on doors.
Mhm.
So if someone were to walk to a door and the door would detect like, okay, the someone wants to go to the door, so the door will open, and then after going to the door will then close. And I wanted to make the system in a way where like if all the doors are closed and the system can go back online, or like the alarm can go back online. Um, and also like kind of apply this to other systems like the AC or the stove,
Mhm.
to help indicate that like if there's other systems that are online and or that are in use and we need to turn off at some point, so that's so that the system can come back on. Um, yeah, that's how I wanted to. That's the theme of my project so far.
Okay, well, let's go back to this project and then what this assembly language program and related to what Nathan is doing, and I'll show another one in a minute. So say you're trying to aggregate two bits of information, the temperature in one room, the temperature in the other room. Here we're just adding them together, but we could be doing something other just than adding them together. We could be seeing if they're below a certain threshold or not. And if they do, that would trigger something. That would be something that we could be doing, and then have the result just go to the console to show that the result if it either passes or did not pass. Does that make sense, Nathan?
Could you repeat it one more time, please?
So let's say, for example, instead of saying enter A and B, you could be saying enter the temperature in room A, the temperature in room B. And then you wanted to say, you wanted to verify that those temperatures are within 5 degrees of one another. I'm just thinking of this off the top of my head. Does that make sense?
Yeah. So like what if it's like when it comes to like if I want to check if the doors are closed, how would I
Okay, then
implement that?
you can have closed, you can either type closed or open. Or if you wanted to have a 1 and a 0, those would be the things that you would be doing for that. Let me open up another program. Um, let's introduce another thing. Um,
Oh, so are you saying like so I manually like type out like that like certain doors are closed or that certain systems
yeah,
are on offline, and then I'll
yeah,
print out like the final result saying like okay, the systems or all the doors are closed, so the system will come back on. Is that what you're saying?
something like that. So
Okay.
it's at a fairly low level. Um, but I wanted you to be thinking about that. So let's look at this one. So here we have a decision, so branch if equal. Let's go to the help here. So BEQ branch if equal, branch to statement at labels address if the register T1 and register T2 are equal. So let's think about this as we're going through here. I kind of picked this in the middle here, but we're comparing T0 and T1, and we have this label here. So remember, um, this is we don't have line numbers, so we can see that we can stay in a certain part of our code until we come up with a decision. And then based on that decision, it's going to tell us what we're going to be doing next. So this could be a feature that you would likely want to be leveraging in your code, Nathan, just to give you a sense.
So I could use like this branch to like
Yeah,
equal to the final result, like saying like if one equals one to the final system, then that's like gonna print out like the all the like the systems online because the doors are closed.
yeah. Well, let's just look at this one line of code to give you an idea how you would be doing this. So if you're familiar with an if statement. If you do this, then you go someplace else. If they're not equal, then it's just going to continue to go to the next step. J is a jump. And so this is how you do a loop. You branch out of that loop if they're equal, and if they're not, it just keeps going back up to this line, and it keeps doing these additions and additions. And so let's go ahead and run this just so people can get an idea of what's going on with this bit of code here. So enter an integer. Anybody want to enter, give me a number you'd like me to use? You can just type it in the chat.
11.
Okay, 11. Okay, the sum of 1 plus 2 plus 3 plus 4 plus 5 plus 6, 7, 8, 9. So the number of the integers is total of 66. And so that's what we see is going on with this program. So we keep incrementing with the integers until we get to n, which is 11. And then at that point, it says, okay, I found my solution, and I break out of that loop. So this is demonstrating what a loop is like here. We have several messages that are here. So let's look at that. And so this is a little bit hard to read. NUMBER, number O of INTEGER. So we see that is laid out there in that first line. That just gives us an idea of this first statement that's here. And so that's we need to be putting the number of integers, and we have another message two for sum. And then we just have a line feed is another thing just to make it look clean on our console. So we have this basic input and output that we're doing with the console. This could be mimicking what's going on with a sensor. So remember the CPU, it's very myopic. All it sees is registers, and whatever a command that is telling it what to do, and it produces that result. We saw that with the arithmetic logic unit. Maybe that's the easiest way to get your head around that for this. Then we have the ability to do a branching. And so basically it compares two registers, and if they're equal, it goes to exit. Otherwise, it continues in this loop. So we can make a loop. And so it's going to be a lower level. You're not going to have as much flexibility of the types of looping commands that you're going to have, but you can still do those basic functional things that we're used to seeing when we write code. Okay? So let me go back to Barak. And so this is what he said is so Barak wanted to do a file directory simulator. And so there's various things that would be involved with that. So this gets gets a little bit involved. And so there's some of you that maybe have taken CS 260 when you're dealing with data structures. And so the abstract data types are tree, stack, hash, and map. And so It's designing a file system simulator that mimics a hierarchy of storing kind of storage kind of like Windows or Unix, using a tree structure to represent directories and files, hash map to associate the file names with metadata, and a stack to handle file navigation, directory traversal to back and forth through directories. That's going to be, Barack. Well, first of all, I think this is a very cool idea. And what I would recommend is that you look at something that you could simplify, at least to in the beginning, especially if you've never done any assembly language programming. That might be something that would be of use to think about. So like maybe a way of doing that, if you were to type and you could maybe be thinking of like a command processing emulator. And so you have a couple of commands that you could be doing. So maybe something like here you're adding two numbers. Well, you could be entering a command like ls, list the directory contents. And so then you could just reflect a message and have a couple of things. And so that would be the list of the items, which would include directories as well as files. And that might be the first way of helping you do that. And then maybe you could do like a CD change directory, and then you could then do the ls command and show that it's at a different level. So what I'm trying to point out for Barack's problem is you have to think at a more basic level when you're thinking about assembly language programming. And once again, work very close to the processor. That's the aim of what this type of capability is meant to accomplish. Barack, maybe you can just give me a thumbs up if you're tracking what I'm saying or what I'm suggesting. Okay, good. Well, why don't you take a shot at doing that? You've seen these two sample programs that I've shared with you. Let's think if we could start to unpack this a little bit. And at least in the beginning, there's like three sub programs for each of these three different parts of our project that I'm wanting people to do. And it's fine and actually preferred if you come up with something and you add a little bit, and then you describe that addition, then you add a little bit more, and you describe that second addition. And so you have a developmental stage of three items that you've done in terms of the capability that you're trying to do with your program. Let's see, let's just pick at random somebody else. Paul, would you like to share about your project, and maybe we can relate some of these assembly language concepts with what you're doing on your project?
But like,
Can you hear me?
how would you,
Yeah, I can hear-
like, in terms of like, is this something that can actually be that are
I'm still not totally sure like exactly how to implement assembly well, because so my like project was with like cards, right? So the main thing I was thinking of like with digital logic, how you can sort of just like run logic checks to make sure certain things like work together, certain like interactions are valid. So I'm not sure like I feel like I don't know how to convert that to like a lower level of assembly. I don't know, like maybe I could like give everything an individual number and then like use those numbers. Perhaps.
Yeah, well, let me help you unpack that. I was having a little tough time. Which one is your project idea?
Number 8.
Number 8, okay. Yeah, I don't know what that is, but I'll just kind of abstract that if for the purpose of just having some illustration right now. Let's just think of just a regular pack of cards, and so playing cards, and so there's 4 types. It's either hearts or spades or clubs or diamonds. And what I'm going to do is just do a way of thinking about that. Is that close enough to what you're doing to just give you a basis?
I think so, yeah, that would work.
Okay, so let me just use that as an example for be thinking about these different things. So the first thing, we have the input and output. So remember, the CPU all by itself, it doesn't know what's going on anywhere unless it's put into the registers, and then it can actually do something with that. Just think of the ALU. Information has to be brought to the CPU for it then to be doing things. Think about a brain. Your brain doesn't actually see, but the information from your eyes goes to the brain, and then it gives you that awareness of what's actually going on around you. Maybe that's an analogy that might help. Okay, so you're going to have some way of sharing that information with your Mars MIP emulator. And so I'm just going to say, what card do you have? And so you have to have two parts, you know, so was it 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King, or Ace. So you're gonna have to have that way that spelled out, and so you're gonna have to have a code for that. If it's 1 through 10, and then a J, a Q, a K, and then an A, maybe you have something like that, and then you want to be putting like, well, is it a spade? And so those would be 2 bits of information that you could be putting. And so you have the value, and then you have the whether it's clubs or spades or something like that. And so thus you have those 2 complementary bits of information that you're going to bring together for that. So I'm going to assume that these cards are going to have some way of where you're going to be able to classify them in one sort or another. And so that you characterize one card, and now you could be characterizing another where you're going to have those 2 inputs. And then you can say, are they the same number? And so then you could be using what we're having here with a branch if equal. So if they're the same value, they're both 10. For example, that's 1 tens of clubs and 10s of diamonds. Then you can be saying, yes, they're the same. Or you would have, so I'm just going to stick with that for the beginning. And so once again, assembly language is you're focusing close to the vest of what a CPU is doing. And so that's how it would be working for that. So Paul, if it's hard for you to go off mute, you can just do a thumbs up if what I was conveying makes sense.
That makes sense, yeah.
Okay, so maybe just first one would be just getting that you input and you put right up to the console what it is that you have been able to ascertain was given to you as a card.
Uh-huh.
Maybe your second level program is you then enter 2 and you do a comparison. And then say for a third level program where you add a little bit more, that would be something of your own choosing that could be getting more specific about what you're trying to do with these cards. Okay? Anybody else wants to offer up what you're doing, and we can walk through this a little bit here? Adam, you want to give us a little bit of input on what you're doing with your project and see if we can relate these assembly language programs to that? And if you have issues going off mute, you can just type it in the chat. That's perfectly fine. Okay, I'll give Adam another minute or 2, but while he's doing it, is what I'm conveying, you can just give me a reaction, a thumbs up if you're tracking with what I'm suggesting of how you're breaking down a part of your project into what you would be doing for assembly language. Is that helping out? Okay, at least got reaction from 1. So for others, does that mean it's still not clear? You can give a thumbs down or something else if you want me to continue to walk through this. Okay, so a few more thumbs up. Okay, that's good. So just wanted to keep checking in and as we move forward. Okay, well, I think what I'll save it for next time, but I also have some other emulators. But they do slightly different things. One starts to give you more of a sense of these commands processing through a computer architecture pipeline, which is a concept we haven't really gotten into yet. And that's will be something I'll reserve for another time. But let me just take a few more minutes to just focus on where we're at. And so on next Tuesday, we'll go over digital logic, and that'll finish up this section in terms of arithmetic and logic. And then we're going to get into the details of how we think about instruction sets. And so let me just go through a little bit more information, talk about our greatest hits part of our summary that I keep coming back to. Then you're starting to get a better sense of how all of these things are working. We have these three elements of a von Neumann architecture: the CPU, the memory, and the I/O. Now this execution is becoming a less of an unknown. We know that this is actually the arithmetic logic unit. We have these different registers that serve different purposes. We know that the instructions and data are in different locations. The Mars MIP emulator helped to point that out. We're just hearing about it, but soon we're going to be getting into the specifics of dealing with the various steps in a pipeline architecture. We talked about the different types of memory that are used for different things in the memory hierarchy. The characteristics of data versus instructions are different. The fact that it's not obvious, but the more cache levels that you have, it performs better, because guess what? You're not always going to have to go to the slow main memory with each one of these caches. It's literally trying to have the best set of data, so it can just have to bounce to the cache, go back to the CPU. But according to the CPU, all it does, it sees registers and then it's asking information from the main memory. It doesn't know if it's already in the cache, and all it knows is it got the result faster, which is a good thing for it to take place. We talked about the way how memory modules are constructed. A lot of times they have sub elements that are actually glued into the integrated circuit. And then what you see are just the outside pins for getting access to that information. We talked about the configuration for a HDD, a hard drive. Talked about a little bit about RAID. We talked about the I/O modules and the different things that it does. It basically does a translation of speaking the language of a peripheral, and then it has to adapt that into what is the language and the way that things are set up in the system bus. That's happening with that. We had a chance to be talking about the hardware and software structure. The software, quote, sits on top of the hardware. There can be some choices about what you're going to do with hardware, or do you want to be doing it in software, and sometimes there can be a partnership. I told you an example that I had a PCIe device that was used for connecting hard drives, SATA hard drives, and it was based on some infrastructure that was part of the kernel. And so with Linux, when all that information was no longer valid, the software portion of the implementation would not work. And so I had to get a new PCIe card for hooking in SATA hard drives to my server. So that's just gives you another thought there. We talked about positional interpretation of numbers. And so we have a decimal number up here, and we can be looking at the same way for binary numbers. Instead of base 10, it's actually base 2. And so I'm showing 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. So, and then having some basic understanding of the conversion between decimal, binary, and hexadecimal is going to be very helpful. You'll see a lot of times that they group numbers into 4. For the arithmetic logic unit example I showed you, we saw these groupings of 4, and that was all that we had. Turns out there were 2 other bits that did some slightly different things, but there was a total of 16 different commands that were used as a basis for that chip. We're now just getting into the details of the arithmetic logic unit. And I like to call that the Swiss Army knife of the CPU. It's reprogrammable, and so you can do the things that you need. We got a chance to be talking about some of the operations you can do. I briefly went over addition and multiplication just to give you some sense of what's going on there. We have these different formats, and so we can have a 32-bit format, 64 and 128-bit format. And guess what? If you have more bits, you're going to have more details for the number, and the range is going to be a lot higher with the exponent part of that number. We're going to be getting into this next Tuesday, but I'll just quickly go over these 2 charts. We've seen some of these basic functions here, not, and or, where I was encouraging you to be thinking about how to use those in your digital design. But there's some other ones here, and these kind of Venn diagrams may be helpful for you to get your head around. And we'll get a reflection on these when we talk about these next Tuesday. And so we saw these in the arithmetic logic unit chart. Here we can be seeing the dot, or just having them together, that's and. The plus is or. You put a line on top of that, that's an inverter. And so these are just the ways of how those are described using algebraic notation for these logic operations. And so here's the truth table. We'll get a chance to be seeing a little bit more about that when we discuss that next Tuesday. Any questions on that? That's just a quick review of the things that we've covered so far. Okay, thumbs up. So I guess that means that you're tracking along with what we've got. So, all right. Well, I think we'll call it a day. That's what we'll cover. And I hope everybody has a wonderful rest of your day. God bless now. Take care.
Thank you, Professor.